Hi there. My name is Tyrone Woods, and today I'd like to talk a little more about some of the exciting progress that's recently been made in understanding the nature of so-called massive seed progenitors for supermassive black holes in the early universe, as well as the exciting observational prospects offered by next-generation facilities to put these models to the test in the coming years. Now, to remind you, when we talk about massive seeds, we're talking about formation channels capable of producing initially 10 to the 4 to 10 to the 5 solar mass black holes, motivated by the discovery of billion solar mass monsters out at around redshift 7. This includes the rapid collapse and coalescence of a dense stellar cluster, or rapid accretion onto a single object, which undergoes a direct collapse, although this is a little bit of a misnomer, as well as other possibly more exotic channels. Now, when we talk about the direct collapse channel, we generally mean a primordial atomic cooling halo bathed in an intense Lyman burner radiation field, with accretion rates of order zero point 0.1 to 1 solar masses per year onto a single or maybe a few objects. Now, this is much more rapid than the thermal timescale for any protostar accreting at such a pace, with profound consequences for the evolution of these objects. Now, thanks to detailed stellar evolution calculations using codes such as Kepler, which can transition to following hydrodynamic timescales at the onset of an instability, we now understand the evolution and fate of these objects as a function of the conditions in the halo, including the point at which they collapse to black holes after reaching the post-Newtonian instability. Critically, for any plausible infall rates in the atomic cooling picture, these objects do not undergo direct collapse without a prior long-lived nuclear burning phase as a rapidly accreting star, with observable lifetimes ranging from tens of thousands up to beyond a million years. Now, this means that observationally, we can go hunting for them. Now, for the runaway coalescence of a dense stellar cluster, we do expect the final fate to depend on the available mass in the cluster and how quickly it can grow from collisions. On the one hand, if we expect a steady, persistent growth on the order of anywhere from 0.01 to 10 solar masses per year, we may expect their evolution and their lifetimes in particular not to differ too greatly from that of the rapidly accreting stars in atomic halos. At the other extreme, if we consider the instantaneous monolithic formation of a single supermassive object all at once, even then we do not find a truly direct collapse for masses below roughly 150,000 solar. So these objects should also, in principle, be detectable. Now, finally, we have also looked at the case of arbitrary protostellar masses and accretion rates, and indeed, in some cases, such as would be feasible in the mergers of gas-rich protogalaxies, as envisioned by Lucian Meyer and collaborators, it may be possible to produce a truly direct collapse supermassive black hole seed, although this is still an area of active research. So what then, we may ask, are the prospects for finding massive seed progenitors directly? For the direct collapse atomic cooling halo scenario, JWST will be able to detect the resulting supermassive stars even out to maybe almost redshift 20, in particular with the benefit of stacking and piggybacking off of, say, planned guaranteed time surveys of lensed environments. At the same time, Martins et al. 2020 found similar results for the case of supermassive stars in protoglobular clusters. Now, in the future, LISA may provide an essential probe for the direct collapse channel, thanks to the growing realization from numerical simulations that supermassive stars rarely appear to form in true isolation, but rather in small N clusters, which will collapse to black holes and then merge at redshifts well before we would otherwise expect to detect such mergers. Indeed, as numerical simulations increasingly probe halo evolution with low to moderate incident Lyman-Werner fluxes, using ever more refined physics, we are finding more and more of a continuum between typical Pop3 star formation and supermassive star formation on the other end, which is very exciting. But I'll close by saying that many of these results were summarized or many others even first hinted at, in a review we put together with the help of a great number of people at a conference in Prato, Italy, not too long ago. And I encourage you to please check it out if you do have time. And in summary, I'll say that we've learned an awful lot about massive seed progenitor evolution in the last few years, and we'll soon have the opportunity to put these models to the test. If you'd like to discuss any of this further, please don't hesitate to drop me an email. And if you'd like to look into any of these papers in particular in detail, I'll note that Woods is far too common a name to be easily Googleable, so please check out my website. Thank you.